All right. Hello, guys. This is going to be our first virtual review video. So, just so you guys have a heads up, the way that I put together this little review session is I went through our 5 Steps to a Five 2023 review book that I gave you all a copy of. And I skipped ahead. Let me check the page that I'm working through right now. I am in the section on one variable data analysis. Okay, so this is basically like the introductory stuff from the very beginning of the course. So I'm not going to review this entire chapter in this video, but I am going to review about half of it. Okay, we're going to review basic vocabulary that you guys see here: parameters versus statistics, discrete versus continuous variables. We're going to review, measures of center, measures of variability. We're going to review shapes of different graphs and distributions. We're going to review how to calculate outliers. I'm basically going to review all the stuff from the beginning of the course before we started talking about the normal distribution. All right. I'm going to save that for a second video. So if you wanted to try and follow along, I'm kind of picking out screenshots of what I thought was the most important to talk about. So it's not like one continuous page by page review, but if you wanted to find some of these diagrams throughout your book while we were working, you could do that. So I just wanted to know that's the source material for these review sessions. And by the end of the review session, we're going to do some practice questions. So I'm hoping that you guys can all at least watch this before Monday so that during Monday we can do some practice questions that relate to the material we covered in this review session. Okay, so that's where I'm going to start. And I just want to kind of double check what you guys can see. All right, so I am just projecting the Jamboard, so you should be able to see exactly what I'm looking at here. Okay. Okay. So the first thing I want to talk about is the idea of a parameter versus statistic, and I've mentioned this many times over the course of the year. But parameters are numbers that are based on an entire population of data. So if I'm interested in studying the heights of students at Veritas Academy, the population mean would be the average height of all of our students. If I was able to interview every single student at the school, measure their height, and then average it, I would have a population mean. And that is a parameter. It's a true number, and there can only be one true mean for the height of students at Veritas Academy, right? If I sample every single kid, right, I'm going to have the truth about our average height. And then there are statistics. Statistics are calculated based off of sample data, okay? So, for example, if I didn't have the time to speak to every student at Veritas Academy and measure their height and average it all out, I could instead take a sample. So maybe I sample 50 students from Veritas Academy and I measure their heights and I come out with an average. That would be a sample mean or a statistic, okay? Because it's not based on all the available information. And from sample to sample, statistics can vary, right? So if I take a sample of 50 kids today and then another sample of 50 kids tomorrow, I will more than likely get different means for each of those samples. Today's sample, just due to random chance, might have a few kids who happen to be taller than tomorrow's sample, for example. So my sample mean today might be a little bit larger than what my sample mean might be tomorrow. Okay. And that could change daily, depending on who ends up in my sample each day. Okay. So that's the difference between statistics and parameters. Okay. Parameters are based on population data. Statistics are based on sample data. Okay. So then we have different types of data. We've been studying different types of data all year. And the two main differences are that some data is quantitative and some data is qualitative or categorical. Both of these words here are synonyms for one another. Okay. Quantitative data is numerical in nature. Okay. But just because data is a number doesn't make it quantitative. All right. It has to measure something. It has to measure something or count something. Right. So if you're thinking about how much or how many, you're probably thinking about quantitative data. Okay. Some quick examples of quantitative data, as you can see right down here. Heights. Okay. I use height a lot. Speed is quantitative. That's a measurement of how fast you're going. Your score on an exam, right? That's a measure of how well you did. Concentration of lead in water. That's like a little more obscure, but you know, when we're dealing with part 2 questions, they usually give us some wacky scenarios, right? But this would be like a measure of how much lead is in my water, right? Temperatures, those are measures of how hot it is. Number of people who are in jail for marijuana possession, right? That is a count. Okay. So if you can measure it, it's quantitative. All right. And then the other data type that we worked with a lot this year would be qualitative or categorical, right? And these two words are synonyms because this data is not numerical, and you could essentially sort subjects or people or objects into categories based on the qualities that they have. For example, gender, right? Gender is a quality. All right. If I'm just going to stay as basic as possible and we're just going to think about two genders here, right? Let's think about male and female. I could categorize our class based on the number of males and the number of females. Or I could categorize our class based on their political party, right? That's a quality about you. Are you a Republican? Are you a Democrat? Are you something different? And I could sort you all into categories based on these qualities. Okay. So those are synonyms. And the last type of, or the last distinction in data that I want to talk about before I move on to some newer slides is going to be the difference between discrete and continuous variables. Okay. Discrete variables are variables that have definite gaps in between the values that that variable can hold. For example, your number of siblings, right? That is going to be a discrete random variable. You can have no siblings if you're an only child. You can have one sibling. You can have two siblings, and all the way out to really any number of siblings, let's say out to 5 siblings. Okay. But you can't have a number of siblings that falls into the gaps between these numbers. Can I have 1.5 siblings? Or sorry, that's not where 1.5 would go. 1.5 would go in here. Can you have 1.5 siblings? Can you have 2.73 siblings? And the answer to that is no, you cannot. You either have a whole sibling or you don't. Okay. And there are lots of other variables that can be considered discrete. For example, how many times have you eaten today? Right? Every meal that you eat counts towards the number of times you've eaten. So you've either eaten once today, twice today, 3 times today. If you eat something, it counts, right? You can't eat 1.5 times a day, right? That wouldn't make any sense. Yes, what's happening here? You're the only one here. Of course I'm the only one here. All right, let's keep cooking here. And then we have continuous random variables, right? Continuous random variables can take on any value in an interval, right? So example, my weight would be an example of a continuous random variable. I can be 200 pounds. I can be 201 pounds, but it's also possible for me to hold any value in between these two numbers. Okay. It is possible for somebody to be 200.1597 pounds. I would have to have an instrument that was capable of measuring to this many decimal places of a pound, but it's possible. Okay. Where that's not possible for number of siblings, it is possible for something like weight or height or speed or time. Okay, I can hold any value within a plausible interval for those variables. All right, so that's the difference between discrete and continuous. Okay, so that's like kind of the intro stuff that we did from the first couple days of school. All right. And I don't want to destroy my whole Jamboard here. So no, looks like I'm going to destroy my whole Jamboard. Okay. So now I want to get into like the meatier part of one variable analysis, which is describing data. And we're going to go through a couple of different types of different data displays. The ones that I have on the screen right now are called histograms, but we're also going to, this is a histogram. We're also going to look at stem and leaf plots in a little bit. We're going to look at dot plots in a little bit. We're going to look at box and whisker plots in a little bit. Okay. So if you're following along here and you can read up top, if you are given the instructions to describe a set of quantitative data, be sure to discuss the shape, the center, the spread, and the outliers. I don't know if they put that part in this little blurb here, right? But if I want you guys, when you're asked to describe data, to remember the acronym SOX, okay? The first S stands for shape, all right? And that's what we're going to focus on this slide. The other three, this is outliers, this is center, and this is spread. The last S is spread, otherwise known as variability. Okay. And we'll come back and we'll touch on these things in a little bit. I want to start with shape. Okay. So if I'm looking at this first graph here, I would describe this shape as approximately symmetrical. Okay. It does not have to be perfectly symmetric for me to say that it is symmetrical. All right. You guys know symmetry. It looks the same on both sides, right? So if I drew like a dividing line down the middle of this thing, you could say it looks roughly equivalent on both sides. Okay. This is an approximately symmetrical shape. All right. This one over here would be considered approximately uniform. Again, it doesn't need to be perfectly uniform. If you throw the word approximately in front of your description, you're covering yourself, right? It's not perfectly uniform, but if I draw a straight line across here, these bars are all roughly the same height, right? So this one is, I would call approximately uniform, all right? Okay. This one's roughly symmetrical or approximately symmetrical. This one's approximately uniform. And then we get to the two down here. Let's focus on this one in the bottom left first. This thing would be considered skewed to the left. It's skewed left because if I draw a smoothing curve over the top, right, you can see this tail is going off towards the left-hand side. Okay, I don't have a picture of skewed right on here right now, but skewed right would look like the same thing flipped in the other direction, right? If I have this long tail off to the right-hand side, this one would be considered skewed right. Excuse my awful handwriting. It's not easy to do with a mouse. And this one would be considered skewed left, okay? And being skewed right or skewed left tells us something about the data, okay? We're going to talk about resistance a little bit more when we do one of the example questions in the back. But just so you guys remember, when I'm talking about measures of center, the mean is easily influenced by very large or very small numbers in the data set. We're going to talk about measures of center in a second, but just as a preview, the mean is very easily influenced by large or small numbers, whereas the median is not. The median is the position of the middle number in the list, whereas the mean is more of a measure of central tendency. It accounts for the values of the numbers in the list. So for example, in this graph down here in the bottom left, I would say that the mean is definitely going to be smaller than the median on this graph. And I'll tell you why in a second, right? But I'll just draw a mean. The mean here is definitely going to be less than the median, okay? The median is just the middle number in the list, right? So I don't have values on these graphs, but whatever values these bars represent on the right-hand side, there's a lot of them, right? And then the smaller numbers on the number line, it looks like there's a smaller quantity of these smaller numbers over here on the left-hand side. So I would say, I don't know, maybe the mean is in like this bar somewhere, right? So I don't know if there's 100 numbers total in this list, right? The majority of those numbers are over here on the right. Less of those numbers are over here on the left. So maybe the median is probably like somewhere in this bar, represents like half the list. But the mean is going to be much more pulled towards the left. That's why it's called skewed left. Because while most of the numbers are over here on the larger side of the number line, you are going to have some values that are much, much smaller than the rest of the values in the distribution. And those small numbers are going to pull the average down. Okay? Flipped in the other direction, if you're looking at my little diagram over here about skewed right, the median is going to be somewhere near the peak in the distribution. So I would say like the median would be like right here, but the mean is going to be pulled to the right. In a skewed right distribution, the mean is actually going to be bigger than the median. Okay? So imagine like this smooth line here. I'll try and clean it up and erase out, right? Imagine, I've given this example in class before. Imagine our average class height, all right, with and without a really, really tall person, right? So let's say before you add a really, really tall person to our class, maybe the average height is like here. But if I add somebody like Shaquille O'Neal to our distribution who's really, really tall, the mean is not a resistant measure of center, right? So if I add a really, really tall person to our distribution, he is going to pull our mean over to the right. Okay? And so that's why this would be called skewed right, because the mean is going to be pulled to the right and it is going to be larger than the median. Okay? In an approximately symmetrical distribution, the mean and the median should be right about the same place. Okay? So if the median is at the peak of this distribution, because it's symmetrical, the mean and the median should be roughly near the center of this graph. Okay? The last thing I wanted to talk about on this slide is the box in the bottom right corner. And this is an example of a bimodal distribution. A bimodal distribution is a distribution that has more than one peak, right? So if I do some more erasing here, whereas this distribution in the top left, it only has one peak, right? You can see it's that bar right in the center. This bar would represent the peak of the distribution, right? But this graph over here in the bottom right, it does have one peak here, right? This is definitely the highest bar on the graph. But there seems to be a separate cluster of data points, right? Separated by this bar right here, which is really low, right? And this separate cluster of data points also has a peak, okay? So I would say that this is definitely skewed to the left. If I drew a smooth line over it, right? It looks like it has a long tail going off to the left-hand side, but I would also say it was bimodal, okay, because it has two peaks. So specifically when you're describing shape, you're going to want to describe two things. If you're looking at a distribution that's either a dot plot or a histogram like this, right? You're going to want to make note of the number of peaks. So it's either unimodal, which is one peak, or it's bimodal. And you're going to want to talk about the relative shape. All right. Is it symmetrical? Is it skewed to the left? Is it skewed to the right? Is it uniform? Okay. A uniform distribution is not going to have any peaks. All right. So this one would be unimodal and approximately symmetrical. Underneath, this one's definitely unimodal and skewed left. This one in the bottom right is bimodal and skewed left. Okay. My little smooth curve here would be unimodal and skewed right because the tail goes off to the right. And this guy would be approximately uniform, right? You don't have to talk about a number of peaks when it's uniform, okay? The next thing that I want to discuss is measures of center. So we talked about shape. Now we need to talk about measures of center. All right, let's start with the least important measure of center, and that would be the mode, right? We don't really use mode often, okay? The mode simply refers to the number that appears in the highest quantity in the list. Okay. So if I have a list of numbers and the number 5 repeats itself the most times, then 5 would be the mode, right? And then we have the median and the mean. Okay. The mean, if you can see by this formula, is the numerical center of a distribution of data. Okay. All of the values in the list are important to calculating the mean. The mean is not a resistant measure of center. It can be pulled in either direction if I have really high or really low numbers in my list. Okay. The median is simply the central number in the list. It is the number in the list that separates the top half of the data points from the bottom half of the data points. Okay. Now, it's relatively easy to find these two numbers by hand, but you won't ever have to do that. And I'm going to show you how to do it in the calculator in a second. Okay. By hand, to find the mean, and here I have an example list of numbers. To find the mean, I would add all these numbers up and divide by how many there are, right? So it would take me a while to add all these up in my calculator, count how many numbers there were, and divide my sum by the quantity of numbers in the list. That's what this formula says. All right, this is a summation sign. It means add all these numbers over here and divide by how many numbers there are. Okay. The median is different. The median gives you the position of the middle number, not the value of the middle number. They are different things. The median will tell you the position of the middle number. This formula right here, n plus 1 divided by 2, okay, gives you the position of the median, not the value of the median. This formula is only useful when the numbers are listed in order. The numbers are not listed in order, then this formula does you no good, okay? It will not tell you the position of the middle number in an unordered list. So this list up here is not ordered. We will come back to when this formula is useful in a little bit, but let's think about if I was taking the AP Stats exam and I was given this list of numbers and I was asked to identify the mean or the median, okay? First, I have to adjust what I'm going to share with you guys. Let me pull up my calculator, and I want to share. I don't want to stop recording. I'll stop presenting for a second. And now I want to present my calculator. Let's present my calculator. Okay, here we go. We're going to present the calculator here for a second. So you guys can't see the Jamboard anymore, I don't believe, but that's all right. I'm going to pull up the Jamboard and I'll talk you guys through it. Okay, so if I want to calculate statistics based on a list of data, what I have to do is I have to hit stat, and I'm going to want to edit a list of data. Now, I already have some data in this list, so I'm going to clear it by hovering over the column heading and hitting clear and enter. Okay, and that'll clear it all out. And I want to put these numbers in the list so that I can calculate the mean and the median and a bunch of other good stuff, right? So I am going to start inputting data into the list, right? So I have a 0 and a 4, 3, 2, 11, 29, 54, 59, 35, 41, 46, 25, 47, 60, 54, 46, 49, 46, 41, 34, 22, and 6. Okay, I have all my numbers in the list. And once I have all my numbers in my list, and hopefully you guys have a calculator at home and you can at least just plug some numbers into any list, right? I don't even care if you don't do the same numbers as me, just to, you know, commit it to memory a little bit. You hit stat, right? Hold on here. You hit stat, stop scrolling, and you edit your list. All right. When you hit stat edit, it brings you to the list. When I want to actually calculate some stuff, I'm going to hit stat. I'm going to scroll over to calc, and I'm going to hit one variable statistics. Okay. And I'm going to make sure that the list that I was given, or where I put all my data, is in list. And I'm going to scroll down to calculate. And it is going to give me all the important stuff. Okay. So I can see here right now, the mean X bar for that list is 32.45 and change. Okay. This is actually giving me the sum of all the numbers in the list. So if I were to add all the numbers up, it would be 714. If I look 2 down at SX, that's going to be your standard deviation. If you are asked to report the standard deviation for a set of numbers on the AP Stats exam, this is the one that you are going to use, okay? The one below is for the population standard deviation, all right? You only use this if you are being told that you have every single number in the distribution. Otherwise, you're going to use this SX number, okay? N is my sample size, right? That's how many numbers did I plug into my list. This calculator is telling me 22. All right. The minimum, I guess there was a 0 in that list. I don't remember off the top of my head, but they're telling me the smallest number in the list was 0. All right. Then you have your quartiles. We talked about quartiles during the year. I'll get to quartiles in a little bit. Okay. So here's your Q1 and your Q3. Again, we'll discuss those in a little bit. My median here was 38. So there it is. The calculator will tell me the median. It will also tell me the max, the highest number in the list. Okay. So that's using the one variable statistics function in your calculator. Anytime you are given a raw list of data and asked to report on things like the mean or the median or the standard deviation, or even if you're asked to find outliers, you're going to need the quartile values. Okay. The one variable statistics function is what's going to do that for you. Okay. So I'm going to leave my calculator now. Now I have to reshare. I'm going to stop sharing my calculator. And I want to share my Jamboard again. There we go. Okay, on we go. So here's an example of when I would want to use, and I just want to make sure I'm sharing, yes, of when I would want to use this median formula, okay? So if I was asked to find the mean of this data set right here, I wouldn't be able to do it, right? This is a histogram. I do not have the specific values for the data in this distribution, okay? I have intervals, right? This is a number line down here. So each one of these bars represents numbers that fall in a specific interval. So if this is 2.95, maybe 2.96, 7, 8, 9, here's 3.0 right in the middle. So this is like 2.98 to 3.1 to just below, anything below 3.2. As soon as I hit 3.2, as soon as I hit the right-hand edge of this box, I'm being counted in the next interval, right? So I wouldn't be able to find the mean of this distribution, but I would be able to find the median because I can figure out how many numbers are in this list, right? So if I was asked to guesstimate the median based on grouped data, this is grouped data, right? The numbers are grouped into intervals. The first thing I would need to know if I come back and look at this formula is I'd need to know the sample size or the number of numbers in the list. So we can figure that out by looking at this distribution. So I'm going to say, all right, I'm just doing my best that this first bar only has one value in it. Okay, so there's one number that falls between 2.8 and just below 3.2. All right, my second bar, if I'm going to draw a line straight across, I wonder if they have a line button on here. Let's see, how do I draw a perfectly straight line? Maybe if I hold the space bar. Nope, that doesn't do it. Okay, I'm not sure. Whatever. I'm just going to do my best to go freehand here. All right. It looks like I would guess that there are about 14 numbers in this bar. All right. This bar, if I'm looking, it doesn't look like it hits 30 to me. I would say that there are 29 numbers in this bar. Okay. The next one, let's call it 26. I think that's above 25. So I'm going to call this 26 numbers in this bar. All right, this one down here, it's getting a little trickier as I get further away, but I'm going to call this 21 bars in here, or 21 numbers in this bar. All right, and let's get a little bit further down. Let's call this one 5, 6, 7. So there are 7 numbers in this bar. And then here, all right, let's see, let's call it 3. Let's call it 3 in that one. Okay. So if you were on the exam, right, and you were given a histogram like this, this is the game you have to play. First, you got to figure out, well, how many numbers total are represented in this chart. So 1 in 14 would give me 15. Let's see, 15 plus 29. 29 and 10 would be 39, plus another 5 would be 44. 44, let's just do some quick math here. 44 and 26, right, is going to give me 5, 6, 7. So that's going to give me 70. Plus another 21 is going to be 91. So I'm up to 91. Plus 7 would be 98. Plus 3 would be 101. So I'm going to guess here. I'm going to guess that I miscounted and there's not 101 numbers. I'm going to guess that there's probably 100 numbers in this distribution, right? So let's go with that. Don't forget about my totals, but let's say I was off by 1 somewhere. We got it pretty darn close. And we're going to say that N was 100. All right. I think I saw in the book that there's supposed to be 100 numbers in this graph. So I must have miscounted somewhere. That's fine. My formula to find the median is N plus 1 divided by 2. So in this case, all right, there's 100 numbers on the graph plus 1 divided by 2. That will give me the position of the median, not the value. So 100 plus 1 is 101 divided by 2, right? Which is going to give me 50.5. 50.5. Okay, I shouldn't have erased all those numbers. That was stupid of me. Go back. Remember 50.5 for a sec. Let me get my numbers back roughly. Okay. So I'm saying the median is at position 50.5. That means it is between numbers 50 and numbers 51. So if I wanted to estimate the median here, I need to find, well, in what bar are numbers 50 and 51 going to fall? So within my first two bars, I have 15 numbers. I roughly guesstimated that there would be 29 numbers in the next bar. So 29 plus 15. Let's figure out how many numbers we would have in 1, 2, the first three bars, right? So 9 and 5 is going to give me 14, carry the 1. So 2 and 1 is 3. And so I only have 44 numbers in my first three bars. But in my fourth bar, there is an additional 26 numbers. 26 plus 44 is way bigger than 50 and 51. So I know that numbers 50 and numbers 51 must be in this fourth bar. So while I don't know the exact value of the median, I know that it's somewhere in this bar. It's somewhere between 3.10 and this is 3.11, 3.12, 3.13, 3.14. Right when I get to 3.15, it goes into the next bar. All right. This is a little hard to tell because this is really small here, right? But I know that the median's got to be somewhere within this bar. So whatever intervals, right, whatever interval this bar represents, that's where the median's got to be. All right. We can do the same thing here. Oh, actually, I think this actually might be the cumulative relative frequency chart for this graph. So I wasn't wrong. There are only supposed to be 100 numbers. So I must have miscounted somewhere, right? I went 1, 14, 29, 1, 14, 29, 26, 21, 26, 21, 7, and 2. So it was right here. I said that there was 3. I said there was 3 numbers in the last bar. There was only 2, right? So that's where I went wrong. But we're going to get the same answer here. We're going to find out that the median should be in this fourth bar, whatever that fourth interval represents. How do I know? Right? They're giving me the frequency in this column, but they're giving me the cumulative frequency over here, right? There's only one value in the first interval, but there are 14 values in the second interval. So this cumulative relative frequency right here, right, is telling me how many numbers are in this interval and up, right? This 44 is telling me how many numbers are in this interval and back, right? So you can see, right, that we have not hit, we said that our median was going to be at 50.5 or between values 50 and 51, right? Well, in my first three bars, I only have 44 values. By the time I hit my fourth bar, I'm up to 70 values. So between 44 and 70 are the numbers 50 and 51. This bar must have the median between 310, or I should say 3.10 and 3.14. Okay? So that is where this formula is useful. This formula you really don't need to memorize. I think you all know the mean is add them all up and divide by how many there are, and the calculator will do that for you. Okay? So let's keep cruising here, all right? I know these are going a little long. I'm going to try and make them as brief as possible, but you got to bear with me. All right? Now we're talking about spread, okay? Spread is how spread apart the data is, okay? There are several different measures of spread, all right? The easiest measure of spread to think of is the range, okay? I don't even have that pasted in here. We don't often use the range, but the range is going to be your highest number in the list minus your lowest number in the list. All right, highest number minus the lowest number. If you're asked to describe a distribution and there's no way for you to figure out what the standard deviation is, then you can use the range, right? The highest number minus the lowest number. That's a measure of spread. We also talked about IQR, and I'll get back to the IQR in a little bit. That's the interquartile range, okay? And it's kind of intuitive if you think about it. If you split something into quarters or quartiles, right, there should be 4 values then, right? There are 4 quarters in a dollar. There are 4 quartiles in any set of data, right? You got Q1, Q2, Q3, and then Q4, right? The IQR represents the difference between Q3 minus Q1, okay? The cutoff for the first quartile, again, we'll talk about this a little bit more later. The cutoff for the first quartile represents the first 25% of the data. The median is the second quartile, and like I said, that splits a data set in half. That's 50%, right? Q3, the third quarter, think about a dollar, right? If you have 3 quarters, you have 75 cents, right? The third quartile represents the cutoff for the first 75% of the data. And then the fourth quartile, we rarely talk about it, but that represents the top number, right? Or the cutoff for all 100% of the data, right? So the interquartile range is the distance between the cutoff for the top 75% of the data minus the cutoff for the top 25%. It gives you the spread of the middle 50% of the data, okay? We'll get back to all that in a little bit. I wish I knew how to make this eraser bigger, but I don't. So such is life. I'll just erase real quick. All right, now we're going to talk real quick again about standard deviation and about the variance. These two numbers are related. The standard deviation is the average distance from the mean. So in order to know the standard deviation of a data set, you have to know the mean of the data set already. Okay. And if you can see down here, here's an example of the calculation for the average distance from the mean, right? It seems to me, if you look here, they're telling you X bar is 6. So the mean of these numbers here, 3, 4, 6, 6, 7, and 10. The mean here is 6, right? If you added all these up and divided by 1, 2, 3, 4, 5, 6, you should get 6, okay? So look at what they're doing underneath the square root sign here. First thing they're doing, whoops, that's an ugly circle. Let's try again. They're finding the distance of every number in the data set from the mean, right? 3 minus 6. 3 is going to be 3 below the average. 3 minus 6 is negative 3. 4, the number 4 in the distribution, is 2 below average. If the average is 6, 4 minus 6 is negative 2, right? 2 of the data points in the list are exactly average, 6 minus 6, right? They're 0 away from average because they are average, right? 7 is 1 above average. 10 is 3 above average. Is this little circle? Oh, no, this is... Okay, never mind. I thought that was going to let me make my eraser bigger. So standard deviation, you're talking about average distance from the mean. Now, we did this experiment in class at the beginning of the year. If I took all the distances from the average and I added them all together, they would cancel each other out, right? So let's do that. The number 3, if the average of this distribution is 6, remember X bar is 6, 3 minus 6 is negative 3, okay? So this number is 3 below average. How about 4? 4 minus 6, that's 2 below average, okay? 6, this happens twice, right? But 6 minus 6, those numbers are exactly average. So 0. 6 minus 6 is 0, okay? And then 7, right? I'll do this part over here. 7 is 1 above average. 7 minus 6 is 1. And 10 minus 6, 10 minus 6 is 4 above average, right? So look at all the distances. If I wanted to try and find the average distance from the mean, I have all my distances, right? Every number that I'm about to put in a box is a distance from the average, right? -3 plus -2 is -5. Plus 0 is still -5. Plus 0 again is still -5. Plus 1 is -4. Plus 4 is 0. So if I took all these distances and I tried to average them, right? When you average a number, you add all the numbers up and divide by how many there are. If I take all these distances and I add them up, they cancel each other out. Okay, that's not an accident, because the mean is the the numerical middle of this list. If I subtract it from every number in this list, all the distances are going to balance out, right? I have numbers whose distances add up to -5, and I have numbers whose distances add up to +5. That's why the mean in this distribution is 6. So you'll notice they're squaring all the distances, okay? And they're not, so we didn't cover this too much. They're dividing not by the number of numbers in the list, but by n minus 1. That's really not such a big deal for you guys to memorize. Just know that the sample standard deviation, Sx, that's the one that uses the formula n minus 1, which is why I'm telling you, when you're looking at your one variable stats, use this number, okay? You are only going to use the standard deviation, the population standard deviation, or this symbol, when you're using the one variable stats button. You're only going to use this symbol if they specifically tell you you have an entire population's worth of data. Okay. So real quick, one last thing on spread. The variance is the number that you get before you take the square root, right? We squared all these distances so that we could add them together without having them cancel out, right? Squaring all these numbers makes them all positive. Okay. So if you don't take the square root, you have something called a variance. And let me clean this up real quick before I make my final drawing here. The square root of the variance is the standard deviation, right? So the square root of the variance will give you the standard deviation. And likewise, if I took the standard deviation and I squared it, that would bring me back to the variance. Not super critical, but it is important for you guys to know that. All right, so the standard deviation basically is the average distance from the mean. Okay, and we're going to get back to that in a little bit. I just want to show you some other common graphical displays, and then we're going to do some practice problems, and I will end this first video. Okay, so first things first, we have stem and leaf plot. Okay, stem and leaf plots are pretty easy. We can look at the one where they give us a key here. All right, the stems, okay, represent each part of a number except for the final digit. So right now, if we're looking at this stem and leaf plot on the right, all right, this one right here, and I'll get rid of this box in a second, but that's the stem and leaf plot I'm looking at. All right, I can count how many numbers are in this list. There's one by counting the leaves, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, right? If I counted all the leaves, I would know how many numbers were in this list. And the key here tells you how to read the stem and leaf plot. Okay. 5, and then there's your, your kind of divider line. And a 0 means that somebody had a score of 50. Okay. If you are asked to make a stem and leaf plot on the exam, you always have to include the key at the end. And I will go over making a stem and leaf plot at the end of this video, but it is pretty easy, right? So I can read the numbers off this stem and leaf plot. The lowest score in the list would be 15. I'm looking at the 1, I'm looking at the 5, I'm putting them together, and I'm saying, all right, the lowest score in the list is a 15. The next score in the list would be an 18. That's the other leaf. Stem and leaf plots are useful because it allows me to kind of get a view of where the data lies in intervals of 10, right? So all the numbers in this top row are in the tens column, right? 15 and 18. All the numbers in this next row are in the 20s, right? 22, 23, 26. There are 1, 2, 3, 4 27s in this data set. There are 1, 2, 3, 4 28s in the data set. There are 3 29s in the data set. So you know, right, that the interval that has the most numbers in this data set would be the interval of 20s, right? And it's visually very easy to see. You could even describe the shape of a distribution based on its stem and leaf plot, right? If I drew a smooth line over this, all right, I would say that this thing is a little bit skewed right, okay? If I didn't have these 50s in here, I would say maybe it's closer to approximately symmetrical, right? But most of the data is in the first 2 rows. And then, you know, I have just a few numbers that are a lot bigger than the rest of the data. They're in the 50s, right? So I would say this thing is probably slightly skewed, right? It's pretty close to approximately symmetrical. So if you are looking at it and saying, you know, I think your smooth line looks kind of symmetrical, I wouldn't fight back too much. All right. I would say this thing is probably slightly skewed to the right, though. Okay. Looking at this distribution on the left, it's the same idea. This thing is definitely skewed right. Okay. If I draw a smooth line over the top, right, this one I would say skewed right. It's kind of the opposite of this one. So yeah, this one's skewed. I'm sorry, I'm saying it wrong. This one's skewed right, right? This one's skewed towards the larger numbers on the number line to the right. This one's skewed right. This one's skewed left towards the smaller numbers, right? Most of the numbers are on the high side. And the long tail, when you draw the smooth line, kind of goes off towards the low side of the number line, right? It's a little harder to see. Tilt your head, though, right? If you just tilt your head, right, so that you make this look like a histogram, right, where these are the bars on your histogram, you can draw your smooth line over the top, and I can see this guy's got to be skewed left a little bit, and this guy's probably skewed right a little bit, okay? And then you have your back-to-back stem plot. So this stem plot down here on the bottom, you can compare 2 distributions, right? So look, they took the tens place and they just have them back to back, right? So quiz number 2, I had a kid get a 15 and a kid get an 18. On quiz number 1, I had 2 kids get a 13. All right. Same thing down here, right? Quiz 1 to quiz 2, I can compare the number of kids who got in the 20s, right? So more kids got in the 20s on quiz 2 than on quiz 1. Right? And I can pull out the individual pieces of data, right? On quiz 2, I had a kid get a 22 and a 23 and a 26. On quiz 1, I had a kid get a 20 and a 25 and a 26, 2 27s and 2 29s, right? On a back-to-back stem plot, when you do the reverse side or the left-hand side, the numbers, instead of going in order from left to right, like you do on the right side of the stem and leaf, right? When you have a back-to-back, the numbers are ordered in the opposite direction, right? So the smaller numbers, no matter which side of the distribution you are, the smaller numbers should be closest to the stem. And then as the leaves get bigger, they go out away from the stem. Okay? So that's stem and leaf plots. All right? And then we have dot plots. We've studied dot plots all year, right? They're all just different visual representations of data, okay? I took the liberty before I started this video to go ahead and plug in the one variable statistics function. So again, that's stat, calc, edit. You put the numbers in the list, and then you hit stat, calc, one variable stats. So you can see here, right? Let's make some marks here. The median, maybe I can change my colors, right? The median on this distribution is 29. So the median is here. One of these three dots here is the median at 29. But the mean, let's see, X bar is 32 and change, right? So 30, 31. The median's over here. So I would say that this distribution is slightly skewed to the right, okay? It's slightly skewed right because these 50s have pulled the mean slightly to the right. In an approximately symmetrical distribution, the mean and the median are roughly in the same place, okay? I believe that this dot plot right here represents this stem plot. It does. They're the same numbers. And I've said before, I thought that this is slightly skewed to the right, and it looks like I was right. These 50s are pulling the average up. So I would say this thing is slightly skewed to the right, okay? I want to erase all these marks now. And just really quickly, I want to show you how the quartiles are splitting the data into the quarters, right? So we know our smallest number was at 15, but Q1 is 27. So here's 25, 26. This is 27. So the first quartile is in here, right? In fact, I can be a little more specific, right? There are 31 numbers in the list, right? We know the median is at 29. So if I do 31 plus 1 divided by 2, that's 32 divided by 2. 32 over 2 is 16. That tells me the position of the median is the 16th number. So I can count them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's it right here. This guy's the median. Okay, he splits the list in half. The first quartile happens at 27. Okay, so if I'm looking below this median, right, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers below the median. They're telling me quartile 1 is 27. It's one of these guys, right? Well, if I have 15 numbers, below the median, okay, I can find the median of the lower half of the list. 15 plus 1 divided by 2. 15 plus 1 is 16. Divided by 2 is 8. Quartile 1 is represented by the 8th number in the list. And if I count them, 1, 2, 3, 4, 5, 6, 7, 8, here it is. There's Q1. And of course, it's right at the value 27, like we said it would be. Okay. And then I can do the same thing for the third quartile. The third quartile is 41. It's going to be the 8th number above the median. So here was the median. So now I'm going to count all the numbers that come after the median, right? So 1, 2, 3, 4, 5, 6, 7, 8. Here it is. It's at value 41, just like the calculator said it would be, right? So the one variable statistics button will tell you the values of the quartiles and the median, okay? And that formula n plus 1 divided by 2 will tell you the position. So if I do n plus 1 divided by 2 for the whole data set, I found the median. Then quartile 1, that's actually the median for the first half of the data. So I just counted all the dots that came before the median, and I found the middle point. That's the first quartile. And then I counted all the dots that came above the median, and I used the same formula again to find that middle point, and that's quartile 3. All right, I'm almost done with content here, and then we'll do some practice questions. Okay, so we have the 5-number summary. Okay, the 5-number summary tells me about a data set. The 5-number summary is represented by the minimum number, the first quartile, the median, the third quartile, and the max. Okay. A box and whisker plot, which is what I have on the page here, okay, is a visual example of the 5-number summary. Okay. So if I wanted to determine what the smallest number in this list was, I would start at the end of the first whisker and go down. So it looks like the smallest number in this data set would have been a 1. The first quartile is represented by the first edge of the box. All right, Q1 on this box and whisker plot is 4. Okay, the median is the number, or is represented by the line between the middle of the box. All right, so in this case, it doesn't look like this falls. Oh, if this is 6 and this is 8, this has got to be, what are we counting by here? 2. So this has got to be like 6 point. It's not, we're not counting by 0.2, 0.4, 0.8. No, we're counting by something weird. We have a weird interval here. Whatever. I don't want to waste time figuring that out. Right? So it looks like my median is slightly below 8, somewhere between 7 and 8. All right. My third quartile, or Q3, is represented by the right-hand edge of the box. And then the max number in the list is represented by the end of the whisker. All right. So min is the end of the left whisker, max is the end of the right whisker, and then you have Q1, median, Q3 in between. Important to note that if there is an outlier in the list, and we're going to talk about outliers in a second, if there's an outlier in the list, it will be represented by a star. And if there's an outlier on either side, right, the outlier furthest away from the data would represent the min and the max. So the edge of the whisker actually gives you the largest or smallest number that's not an outlier, right? So in this case, if there was an outlier here, this would be the largest number. And if there was an outlier on the left, this would be the smallest number. Okay. So how do we calculate outliers? Okay. So we can see here that outliers, these are the outlier formula. Okay. There's a separate formula for finding outliers on either side. Okay. We have outliers on the high side. We have outliers on the low side. Okay. To find outliers on the high side, the IQR, remember, IQR is Q1 minus Q3. So the IQR is basically represented by the width of the box. If you multiply that value by 1.5, okay, 1.5 times the IQR, and you add it to Q3. So if I take this box, the length of the box, multiply it by 1.5, and I add it to the high side of the box, I will find the cutoff point for an outlier. And it's pretty much the same thing for outliers on the low side, okay? If I take 1.5 times the width of the box and I subtract it from the low end of the box, I'll see the cutoff point for any outliers on the low side. So we can practice by using this distribution right here real quick. We can see that whoever made this box plot said that there was an outlier all the way out here at the number 20. Let's use the formula to verify if that's true. All right. First, now I guess I really have to figure out what we're counting by, right? So I got a distance of 2 separated by 1, 2, 3, 4 jumps. So I mean, they're not doing a very nice interval here. They're not going to make it easy for me to approximate, right? So 2 divided by, right? So are we jumping by halves? So this is 4.5, this is 5, this is 5.5, this is 6. Okay, I'm just stupid. We're counting by halves. I should know that. I should have been able to figure that out in my head, right? So if we're counting by halves, right? If if we're counting by halves, this has got, if this is 8, this is 8.5. This is 9, this is 9.5. If this is 9.5 and this is 10, it looks like Q3 is 9.75. Okay. And on the low side, it looks like Q1 is represented by 4. So if I wanted to find out and verify if this was an outlier, okay, first I got to find the IQR. The IQR is Q3 minus Q1. So if I have 9.75 minus 4, okay, that's 5.75. That is my interquartile range. Whoops. 5.75. That's my interquartile range. That is the length of this box. Okay. I need to multiply 5.75 by 1.5. All right. Here's my 1.5. Okay. So 5.75 times 1.5 is 8.625. Okay. So I know that Q3, right? That's the first part of my formula, is represented by the number 9.75. And I know that 1.5 times the length of this box, or 1.5 times the IQR, is 8.625. So plus 8.625. Okay. This is going to give me the cutoff for outliers on the high side. If there's any numbers in the list bigger than this value, so 8.625 plus 9.75 gives me 18.375. Okay, this is a cutoff point. If any number in the list lower than 18.375 is not an outlier. Anything greater than this is an outlier. So if this is 18 and this is 18.5, 18.375 has got to be like right in here. Okay. So that's why, since there was a number 20 in this data set, that's why they did not extend the whisker all the way out to 20. They made 20 its own dot because it was higher than the criteria needed to be an outlier. Okay. It looks like the lowest number in this data set was 1. But you'll notice they didn't make 1 an outlier. They let the whisker go all the way to 1. Why? Because the formula for the cutoff for outliers on the low side is Q1 minus 1.5 times the IQR. We already figured out that the IQR was 5.75 and 1.5 times that was 8.625. So think about it. Q1 minus 1.5 times the IQR, or 4 minus 8 and change, 8.625, is a negative number. So in order to be considered an outlier in this list, the number would have needed to be negative. Right? So there's your outlier formula. So now we're going to do some practice questions, and then I'm going to end the video. I know it's long, but I'll be able to make later videos shorter. That's probably a lie. But just watch, because I want you to get a 5. And if you watch these videos, you're going to get a 5. Okay? Let's do some practice questions quick. You can pause here, try and answer it, and then see what I do. Okay? So it says the shape of this graph could best be described as. So if I was looking at this thing, A says mound-shaped and symmetric. I would say no, right? This is definitely not symmetrical, right? There's a gap here in the middle, and this cluster on the right-hand side does not look like the cluster on the left-hand side. Okay. Let's keep going here. And just for you guys to follow along, this under practice problems is number 7. Okay. So if you're looking in your review book at the end of this section, right? If you go to the end of one variable analysis, I'm looking at 7. Practice problem number 7. All right. So let's see what else. Bimodal. I actually wouldn't say that this thing is bimodal, even though there's a gap. here, right? This still looks like the peak to me. It doesn't look like there's a separate peak in here. These are all far lower than the peak on the left-hand side, and these are all roughly the same height. So I wouldn't call this bimodal. If this bar like was peaking up pretty high like this, then I would say this thing was bimodal, but I would say that's not the case here. All right, skewed to the left means the tail goes off to the left. So let's see here, right? I'm going to draw a smooth curve over this, right? And to me, it's pretty clear. This thing has to be skewed right. And if you check the answer in your review book, you'll see that it is skewed right. Draw a smooth line over the top. You could do it with your pencil. You could do it with a finger, right? And you're going to see that the tail on the right-hand side is much longer. So this thing's got to be skewed right, all right? Let's do some more practice questions. All right. So again, if you want to pause, check it out, you can pause, okay, and try and answer the question on your own, and then I'll give you the answer. Which of the following statements are true? The median is resistant to extreme values. That's true. The mean is resistant. I'm sorry. The median is resistant. The mean is not. Okay. All you have to do to determine whether something is resistant or not is just think about what would happen if I added one very big number to the list. Adding one very big number to a list will only shift the median over by a tiny amount. Remember, the position of the median is n plus 1 divided by 2. So if I make my sample size 1 larger, the position of the median moved over by 1 divided by 2, or half a place value. So the median is very resistant to extreme values. The mean is absolutely not resistant to extreme values. If I have a bunch of small numbers that have an average of, I don't know, 3, and then I add the number 100 to the list, the mean is going to get pulled way up, okay? Because the number I added to the list is so much larger than what the old mean was. So the mean is not resistant to extreme values. Standard deviation is also not resistant to extreme values. Standard deviation is not a resistant measure of spread, okay? So anything that involves the mean as a calculation is non-resistant. So the mean is not resistant. Standard deviation is not resistant, okay? Range is also not resistant because range is the highest minus the lowest number. So if I change the highest or lowest number in the list, the range is definitely going to change. Numbers that are resistant are the median and the IQR. The interquartile range is a resistant measure of spread because the quartiles have to do with position, right? So this one is going to be A1 only, right? Median is resistant. Let's go on. This one's pretty tricky. This is question 1 off of where? Where did I get these? Question 1 off practice problems, okay? So it says the following list is ordered from smallest to largest. Which of the following statements is true? All right, so we got to reason this one out together, right? They give us an incomplete list of numbers, right? They repeat the number y 3 times, so they're not telling us what it is. Because they're using the same variable, I know that whatever that number is, it's the same number being repeated 3 times, okay? And I know it's got to be somewhere between 30 and 33 because they told me that I was looking at an ordered list. Okay. So let's look at these things. All right. The mean is going to be greater than the median. I would say that's definitely true. How do I know that? I'm thinking about the nature of these numbers in my head. All right. Look at the list. It goes from 25 to 33. We don't know what these values are, but they got to be somewhere between 30 and 33. All right. The mean here, if you forgot about the last number in the list, the mean here is going to be somewhere between 25 and 33. But if I add 150, the mean is going to get pulled way up, okay? Way up, because 150 is so much larger than even the next highest number of 33. But the median, we can think, how many numbers are in this list? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 numbers in this list. N plus 1 divided by 2. 9 plus 1 is 10 divided by 2 is 5. The median is going to be the fifth number in the list. 1, 2, 3, 4, 5. Right? So there's your median. Do we know its exact value? No. I know it's somewhere between 30 and 33 because they told us this list was ordered. So the median is somewhere between 30 and 33. The mean's going to be way above that because this 150 is pulling the mean way up. So 1 has to be true. All right. This says, number 2 says the mode is 26. I see the number 26 appear twice, but I see the number y appear 3 times. So whatever y is, that's the mode. So 2 is not true. And 3, there are no outliers in this set of data. Now, again, you probably aren't going to be able to use the formula Q1, Q3, Q3 plus 1.5 times the IQR because they don't give you the complete list of data. But if you just think about it, right, 150 is so much further away from the rest of these numbers that it's definitely an outlier in the list. So this is A. And if you look at the answer choice in your textbook, they'll tell you the same thing. Okay? Even if you substituted in the highest possible value for y, right? Let's say y was 33, and you plug this into your calculator and you did 25, 26, 26, 30, 33, 33, 33, 33, and 150. And then you took the quartiles and you did the formula, you would see that 150 is just way too far away. All right. Let's keep going and doing a few more. This one, Mickey Mantle played with the New York Yankees. He had the following number of home runs in each year. Are there any outliers? All right. Are these in order? No, they're not in order. So in order to keep this video just a little bit briefer, I'm just going to explain to you what you would have to do to get this right. Okay. You have to take these numbers. You have to hit stat. All right. So you can practice at home. Stat, edit. Okay. Put the numbers in the list. Then go to stat, calc, one variable stats, right? And use your formula. Okay. The one variable stats is going to give you, I'm very bad at writing with the mouse, but that's all right. The one variable stats function is going to give you Q3. It's going to give you Q1. Use the formula from earlier in the slides. I don't want to rewrite it again, but here are your formulas. Q3 plus 1.5 times the IQR. Q1 minus 1.5 times the IQR. All right, there you go. Let's see. Now they want me to make a stem and leaf. Okay, I'll make a stem and leaf quick for you. All right. So if I'm looking at this, I'm not going to do all this blah, blah, blah that they want me to do here. I'm just going to make a quick stem and leaf, right? I'm seeing these are Mickey Mantle's home runs, right? He has hit anywhere from like 13 home runs through a quick scan to somewhere in like the 50s, it looks like. So here's my separator. They're all 2-digit numbers. So the first digit is going to be the tens place. So 1, 2, 3, 4, 5. Right? Then I would go through my list, right? I'm looking for all the times he hit home runs in the teens. He did 13. He did 15, 19, and 18. So now I'm going to order those leaves, right? It should go 13, 15, 18, 19, right? And then I would go through and I would do that for all the 20s. I would look for all the times he hit home runs in the 20s, and then I would order those leaves. Whoops, I shouldn't have put a 1 in front there. That was stupid. That should just be a 9. And I would write the ones place in order in the leaf section. Okay, I would label this, right? Mickey Mantle. I'm going to abbreviate Mickey Mantle's home runs, right? I'm going to avoid writing whenever I can. Mickey Mantle's home runs. And then I would give a key, right? You got to give a key. All right. And the key is easy. You just say, all right, 1 separator, give one example. And I'm saying, all right, this is equal to the number 13. Okay, that's making a stem and leaf plot, no big deal. And then let's finish with a part 2 question, and then I will stop here, right? So it says, 2 large corporations, A and B, hire many new college graduates as accountants at entry-level positions. In 2009, the starting salary for each entry-level accountant was $36,000 a year at both corporations. Each corporation data was collected from 30 employees who were hired in 2009 as entry-level accountants and were still employed 5 years later. So again, just to give you some tips on how you would do this, okay? Write a few sentences comparing the distributions. I need to compare using shape. Actually, I wouldn't even do shape here because these are box plots and it's hard to tell. But I want to do the other things. So measures of center, you would use the median because that's what you could see on a box plot. Okay? You would say that the medians are about the same, right? Use comparative words. The medians are about equal. For spread, you're going to say the spread at corporation A is greater than the spread at corporation B. You could use 2 measures to prove that. You could use range, which is the highest number minus the lowest number for each corporation. Or you could look at the interquartile range, which is represented by the length of the box. Okay. Both of those statistics favor corporation A. They're both bigger. So I would say, the centers of each distribution represented by the median are about equal. I would say the spread at corporation A is bigger than the spread at corporation B, right? And then I would be some specific, and I would either talk about the range or the IQR. All right. Corporation A has 2 outliers, where corporation B has no outliers. Okay. And that's how I would compare the 2 distributions. I'm always thinking about SOCs. All right. Shape, outliers, center, spread. In the case of box plots, ignore shape. Some places will tell you to use shape. You can't really tell the shape from the box plot. All right. It's hard. Based on the box plots, give 1 reason why you might choose to accept a job at corporation A. I might choose to accept a job at corporation A because corporation A has people that are making more than anybody else at corporation B, right? So anybody who happens to fall in this region over here, right? If you were one of the 2 outliers or somebody at the end of the whisker on the right-hand side here, you have the chance to make more than any single person at corporation B. So that would be my justification based on the box plots. Why would I want to go at corporation A? Because corporation A gives me the possibility of earning more money than is possible at corporation B. All right. What's 1 reason that I would want to work at corporation B? Well, the floor at corporation B is higher than the floor at corporation A, right? So 1 reason I would want to work at corporation B would be, well, the smallest salary at corporation B is higher than the smallest salary at corporation A. So if I'm worried about like my floor, I would want to work for corporation B, right? Because the lowest salaried person at corporation B makes much more than all these people in here. Okay. And that's it. That's what I got. I'm going to cut it off here because I know this is pretty long. So I'm going to try and make many more, both this weekend and in the coming days. So I hope that you guys found this useful.